hello and welcome back to CS 500 Design and Analysis of Algorithms. We are in Chapter 10, Designing and Analyzing Memory-Efficient Algorithms. In particular, we have designed a very memory-efficient algorithm for Boolean matrix powering. Namely, raising a n times n Boolean matrix to the kth power can be done using only log k times log n bits of working memory. Sublinear amount of memory, and the two tricks that we employed in order to achieve this highly memory efficient goal is, first, we didn't store the input matrix. Recall that the input matrix, n times n matrix, has n squared Boolean entries, bits. So storing that would immediately destroy our goal for a sublinear memory algorithm. So that's why we agreed to consider the input matrix to be given in a separate area of memory, which cannot be used for intermediate calculation. It's read-only memory, and it doesn't count towards the use of the working memory of the algorithm. That was our first trick. Technically, the specification of the problem. Our second trick, also pertaining to the modification of the specification of the problem, was that we're not asking for the entire matrix, the Boolean matrix raised to the kth power, to be output, not the entire, again, n square n matrix. That would again require n squared bits of memory. Instead, we changed the problem specification such that the output consists of any desired entry, a single bit of the resulting matrix, and the user, the input of the problem specification, can choose which entry, maybe the entry in the lower right corner or in the upper left corner, coordinates of the entries, so that the output consists of only one single bit. And these were the two keys to our memory efficient algorithm. So let me start the screen sharing with a slide recalling this memory efficient algorithm using only log k times log n bits of working memory when the input Boolean matrix is not considered to use working memory, and when the result is not the entire matrix, but any desired entry, what we call entry-wise n times n Boolean matrix powering. And then we proceeded to apply that memory efficient algorithm to obtain memory efficient algorithms for graph reachability. So graph reachability, remember, we're given a directed graph with n vertices like this. And we're given start and target vertices S and T and the distance. And the question, can we reach the target vertex T from the source vertex within at most k steps using only the directed edges of the graph? And again, in order to allow for a sublinear memory algorithm for this problem, we change the specification to say that the input graph is not supposed to be stored in the working memory of the algorithm. It's provided in some other separate part of the memory, only read-only access. And that can be accessed via queries, maybe asking for two given vertices, any two given vertices u and w, is there a directed edge from u to w or not? And observe that with the usual way of encoding the graph using an adjacency matrix, a Boolean matrix, this is exactly what corresponds to looking up an entry in the row number u and column number w, whether this entry is 1 or 0 corresponds to whether there exists an edge from U to W or not. Now let's recall a classical standard algorithm for solving graph reachability, and this algorithm is of course Dijkstra. We call Dijkstra is kind of a wavefront algorithm. It starts with a source vertex. Source vertex is reachable within 0 steps. Then it considers all immediate neighboring vertices to the start vertex. These are reachable within 1 step. And then it proceeds to the neighbors of these neighbors. These are vertices that are reachable within at most 2 steps, and so on, wavefront growing. So this algorithm stores the vertices that are currently reachable, and in each phase, it updates the list of vertices that are currently reachable. And in order to encode one vertex, we can store each vertex using log n bits, or we can use an array of bits, n bits, that each bit says whether the vertex corresponding to that position in the array can be reached yet or not. That's a typical data structure for maintaining this wavefront. So that means that Dijkstra stores roughly n integers of log k bits. And our goal is to improve that memory consumption. And yeah, since we already have this algorithm for Boolean matrix powering, we're going to use that. And we're going to use the classical observation, which you probably have already learned in discrete mathematics, that well, the original adjacency matrix captures which vertices can be reached within 1 step, namely whether there exists a directed edge. And more generally, the kth power of the adjacency matrix captures whether and which vertices can be reached within k steps, or at most k steps, if we consider the graph to have self loops, or equivalently, if you consider the adjacency matrix to have ones on its diagonal. So by simply applying the algorithm for memory efficient Boolean matrix powering, we arrive at a similar algorithm with similar memory consumption for deciding the directed graph reachability problem. Comes basically for free. And this raises, remember, our virtues of computer science: design, analyze, and try to prove optimality. This raises the question whether our algorithm is optimal or not. I mean, how far could we realistically expect to further improve the memory consumption? Well, maybe we could boil it down to log n. Maybe observe that k can be at most n, right? Any vertex that cannot be reached within n steps cannot be reached at all. So in the worst case, the memory use of our algorithm is log squared of n. And a possible improvement would be only log n not squared. And a very celebrated result of Omer Reingold from 2008 indeed achieves this. Reingold devised and analyzed a very, very sophisticated algorithm for deciding graph reachability in the above sense using only log n bits. But his algorithm works only for undirected graphs, for undirected reachability. So for undirected reachability, indeed, one can improve the memory consumption from log squared n to log n, but this algorithm and the underlying graph theoretic concepts are so involved that they go beyond the purpose of the current lecture. Now let's look back at the cost that comes with our memory efficient algorithms compared to, for example, Dijkstra, right? So our algorithms use much less memory, but this memory saving comes at a cost, namely a drastic increase in running time. Namely, the paradigm that we use implicitly is forget and recalculate intermediate results. Don't store intermediate results to save memory. Instead, forget them, and whenever needed, recalculate them. And intuitively, that can lead to a significant increase in running time. And now let's analyze that increase in running time. Let's analyze the running time of our memory efficient algorithm. Maybe let's analyze the running time of our matrix powering algorithm. And for simplicity, we suppose that k, the exponent, is a power of 2. In this case, remember the matrix powering proceeds by repeated squaring. In this case, we already have even powers, and not the special case when there's an odd power. And let's, last time we devised recursion for the memory consumption, and now let's devise a recursion for the runtime used by this algorithm, not by a runtime efficient algorithm, but the running time used by our memory efficient algorithm. And this memory efficient algorithm, recall, whenever it needs the entry in the, to square the matrix X, whenever it needs the entry at position I, L, it will make a recursive call to calculate that matrix, which in turn, in general, is the square of another matrix. And when it needs the entry XL, J, it also makes a recursive call. So the memory use can be reused for this recursive call and for this recursive call, which resulted in the very little memory use. But the running time for this call and the running time for this recursive call must add up, so that the running time here is for raising to the kth power is the running time for raising to the k over 2 power, plus the running time for raising this over to the k over 2 power. Observe that this is going to be the same matrix, but different entries, and according to our paradigm, the recursive call, this one returns only this entry. So we need to make another recursive call to recover this entry of the same matrix. And then there's this big disjunction, big sum of n terms, so that this corresponds to an outer loop of n iteration. Again, memory-wise, this is very efficient. We only need log n bits to store the counter L, but in terms of running time, this is n iteration. And when solving this recurrence, which is a good exercise, it turns out that the running time becomes super polynomial, sub-exponential, but more than polynomial, because the running time is n to the log k exponent times k. So the exponent to n is not a constant. It's a logarithm of k, or in the worst case, when k is n, it's n to the log n running time. So the lesson to be learned here is saving memory is possible using this forget and recalculate paradigm, but it comes in general at a cost of increased and possibly drastically increased running time. So now let's move on to apply this, namely to consider parallelizing memory efficient algorithm to our related efficient parallel algorithm for graph reachability. So this memory efficient algorithm uses log k times log n bits of working memory. And recall that in chapter 9, we also had devised parallel algorithm with very fast, with only parallel running time, that is depth, log n times log k. So both seem to somehow be connected for this particular problem, graph reachability. And it turns out this is no coincidence. This holds in a very general setting, namely that memory corresponds very tightly to parallel time, which is an observation, a theorem, famous theorem made by Alan Borodin in 1977. So here you see an old picture of Alan Borodin, maybe during the time when he devised that theorem. Here's a new picture of Alan Borodin and a very recent one where he was awarded the Order of Canada in 2022, a very high merit of Canada. So the statement of Borodin's theorem says that any algorithm whose sequential running time is T of n and which uses S of n memory bits, so memory and sequential running time, yields can be converted to a parallel algorithm, namely a circuit, whose depth, that is the parallel running time, is S of n, the memory use of the sequential algorithm, times the logarithm of the sequential running time. So the sequential running time gets accelerated exponentially from T of n to log T of n using parallelism. And in a sense, the only obstacle to this efficient parallelization is the memory use, which translates here linearly. And if you now reconsider, this is exactly what we've obtained for our graph reachability problem, and thus generalized to many other problems, turning memory efficient algorithms to efficient parallel algorithms. And before we look at the proof of this result, very surprising proof, very surprising theorem, please have a look at the time frame. So Borodin devised this efficient parallel algorithm, generic algorithm, in 1977, 6 years before the Apple IIe computer became available, far before the advent of parallel computing that we're familiar with nowadays. A true example of visionary computer science thinking ahead of contemporary technology in general and abstract terms. And I will illustrate now, when we look at the proof, why this is such a impressive and abstract approach and a new perspective on algorithms in general that arises from Borodin, namely the so-called reachability method. So remember, we have here a directed graph, and we want to apply our efficient parallel algorithm for graph reachability to the algorithm with the sequential time T of n using S of n memory bits. And to this end, we consider a particular graph associated with the initial algorithm, namely the so-called configuration graph. We'll say more about the configuration graph on the next slide. For now, let us just record that whenever the algorithm with memory use S of n, then the corresponding configuration graph has 2 to the O of S of n vertices. So exponentially many vertices, exponential in the memory use. It's going to be a large graph. On the other hand, remember our parallel algorithm here, the parallel runtime is only the logarithm of the size of the number of vertices. So the log n here becomes indeed O of S of n, the first part of the result. The second part is that the configuration graph, which I will explain on the next slide, turns out to have precisely two end configuration, one in case that the algorithm accepts and one in case that the algorithm rejects. So we're talking about algorithm for decision problems. When the algorithm says yes, then it corresponds to an accepting configuration, one designated node in this huge graph. And if the algorithm says no, if it rejects, then that corresponds to another, again, unique node in this huge graph. And thus we can translate the original question, does the algorithm accept particular input, yes or no, translates to the question whether there exists a path in this huge graph from the unique starting configuration to the unique accepting configuration. And since we know that the running time of our algorithm is promised to be T of n, that means the number of steps, the length of this path, the number of edges traversed, will be at most T of n. So that's okay. And now observe how k enters in our parallel algorithm, the logarithm of k. This corresponds then to the logarithm of t. And this explains this kind of strange and flipped dependence. Sequential time becomes logarithmic and memory use becomes linear, namely because the memory use first becomes exponential, the number of vertices, and then logarithm again in the parallel algorithm, whereas the sequential time simply becomes logarithmic here. Okay, now I've already talked a lot about configuration graph. It's time to actually introduce the configuration graph. What is the configuration graph? Imagine a configuration graph of a program or an algorithm to be the collection of all snapshots of its memory, that is, of its variables, together with the current program counter. So one node, any node in the configuration graph, is a current snapshot. And when the algorithm makes one step as a thought experiment in symbolic execution, if you like, then that corresponds to it following an edge from one node to another, from one snapshot to another. Okay, so every such node corresponds to a snapshot, and some snapshots can be reached and others can never be reached, maybe because some memory configurations will never occur during the actual execution. And what we can immediately see is that if the algorithm has S of n memory, then the memory can have 2 to the S of n possible configuration, and therefore the number of vertices, number of nodes of the configuration graph is indeed at most 2 to the O of S of n. O of S of n, because we additionally have this program counter, which is also required to fully capture a snapshot, namely snapshot in the sense that if we freeze program execution corresponding to being in one node, and then we resume, then the program counter tells us the next step and thus the successor node. Now let's talk about designated nodes in this configuration graph. One designated node is the start configuration. Initially, we agree that all variables, all memory in our algorithm is reset to 0, except for the input, designated input variable, which contains the input argument, maybe some integer encoding the input. So that means for different inputs correspond to different start configuration, correspond to different nodes in this graph, but all inputs that we consider here must have the same length, namely the same length n. If we consider a different input length, then that's going to be a different graph, because then that's going to correspond to S of n plus 1, and t of n plus 1. But if we fix n, then still this graph captures many different computations, namely for any input of length n corresponds to a different initial node, the initial node start configuration. Another important designated node in that graph is the n configuration. And as I said, there are two n configurations. Well, actually, there are many n configurations, namely the program can end with many possible memory configuration, but it is no loss of generality, and we will suppose that our algorithm, our program, just before terminating, it erases its entire memory, so that at the end, when the program ends, the n configuration is all the same except for this one small difference, namely accepting end configuration and rejecting one bit. We don't erase namely the result of the algorithm for the decision problem. That means our configuration graph will have two terminal nodes, one accepting and one rejecting. And finally, observe that any single step of this program, of this algorithm, corresponds to following one directed edge in this graph. If we consider deterministic algorithms, then that means that the graph consists only of paths. There's no fork in the configuration graph of a deterministic algorithm. If we consider non-deterministic algorithm, or if we consider randomized algorithm, flipping a bit or making one non-deterministic choice corresponds to a fork in this graph, to a node having two possible different successor nodes. But for deterministic algorithm, it's just, the graph is just a union of paths from different start nodes, start configurations, to one of the two possible n configuration, the accepting and the rejecting one. And thus, the original question, whether our algorithm accepts or rejects the input, whether the decision problem has the answer yes or no, translates to the question whether there exists a path of length at most t of n from the unique start configuration corresponding and encoding the input to the unique accepting configuration. And for this, we have this efficient, very efficient parallel algorithm. So you see that how this configuration graph and the reachability question gives an entirely new and highly abstract perspective on algorithms, right? So we used to consider algorithm as a sequence of instructions and possible loops. But from this perspective, an algorithm is an implicit, possibly huge graph, and each step corresponds to following an edge in that graph. How to obtain that parallel algorithm? It's not that you take the original memory efficient algorithm and shift around the instructions so that many of them can be executed in parallel, but instead the original algorithm gets translated into this configuration graph, and then a parallel algorithm is put onto this configuration graph, and the original algorithm is kind of entirely mangled up. It doesn't have to be this way, right? It just says there exists parallel algorithm with this running time, but there could be other parallel algorithms with the same running time that can be derived by rearranging the original instructions. But in general, Borodin's theorem is much more abstract and thus much more general. Okay, so that concludes our discussion of Borodin's theorem and the celebrated reachability method, which later turned out to have many other applications. For example, the famous NL versus co-NL problem solved by Immermann and Selepcheny also is a variant of this reachability method, or Savage theorem, also reachability method. That said, let's now move on to another chapter of memory efficient algorithms, namely memory efficient algorithms for streaming problems. Streaming problems arise when we're asked to process huge streams of data that rushes kind of by, like gigabytes or terabytes, and there's no way of storing that. Consider, for example, a router, right? Internet router easily processes terabytes of data every day, and there's no way to store that, but it can collect some statistics about the data. So here's a schematic picture. Here's the stream running by, and the stream processor receives a query to get some information about the stream, but it has very limited memory, and thus is supposed to store only very little about the stream, just in order to be able to answer that query. Formal specification considers input sequence here of capital N entries, so indexed with small n running up to capital N. But let's say that the entries of this input sequence, the streams, are small integers in the range from 0 to m-1. So that storing one entry in that sequence can be done using log m bits, capital M. What are some problems, some questions that we might be asked to answer about that input stream? One question is the counting problem. So for the counting problem, we're given another input integer in the same range, and we wonder how often does that integer y occur in that sequence. We'll formally output the cardinality, the number of indices indexing that sequence, where the current corresponding entry in the sequence is equal to the given argument y. Well, that's one problem. And it can easily be solved using sublinear memory, that is without storing the entire stream, namely by implementing simply a counter for that, right? So we count how often have we seen y so far, and whenever the next entry in the stream passes by, we compare this to the given y, and if it agrees, then we increment the counter. Now, how large can that counter become in the worst case? The largest value of the counter arises when every entry in that sequence is equal to y. Then that counter runs up to capital N. And so in order to store that counter, log n bits suffice and are necessary. So that's already a sublinear memory algorithm for the counting problem in streaming algorithm. Observe that for this algorithm, the stream needs to be passed only once. There are variant of streaming problems where the stream can or must be looked at twice or a constant number of times. This is not applicable maybe for internet routers, but for example, for searching statistics stored on a magnetic tape, right? Remember, magnetic tape takes a long time to rewind, but once it is rolling, then the data comes in very fast. So imagine that this magnetic tape can be read and scanned once, and then if the stream algorithm needs a second look, rewind, and then look at it a second time. So constant number of passes is a variant, but here we can get away with only one pass. Now let's consider a variant of this counting problem, namely the sum problem. So in the sum problem, we're asked to calculate the sum of all entries in the stream. And again, this can be done using a simple accumulator. that stores this partial sum, and whenever the next entry comes up in the stream, add that to the accumulator. So this algorithm, streaming algorithm, also suffices with one pass. We want to know how many bits do we need for that algorithm, and that corresponds to the question, how large can that accumulator become? In the worst case, all the entries in the sequence are as large as possible, maybe something like m or m minus 1, so that we have capital N times value capital M, and the number of bits to store capital N times capital M is log N plus log M. So that's streaming algorithm for the sum problem. Now let's further generalize the sum problem, not only adding the entries of the sequence, but adding powers of the entries. And this is relevant for second and higher moments. So the sum, calculating the sum can be used to calculate the average, right? Dividing by capital N after the stream is finished. And similarly, dividing this power, the sum of squares, the sum of cubes, corresponds to second and third moment statistics of that stream. And again, the essence is how large can that accumulator become? And it can become at most n times, and each times m to the k, so that the binary length is log n plus k times log m. That's our memory efficient streaming algorithm for sum and for power sum problem. Now let's look at another problem, namely counting the number of distinct entries in the streams. This is sometimes called the F0. So we count, we denote, abbreviate with CY. How often does Y occur in that stream? We have an algorithm that calculates that, but it only calculates that for one single given Y. We're interested in how many Ys, distinct Ys occur here, or put differently, for how many Ys is this quantity strictly positive? And what doesn't work is calculating this quantity Cy for every Y, because remember we have capital M different Ys, so that would mean a linear memory algorithm, linear in capital M. That's the obvious answer. Having a linear algorithm, storing all the CYs, maintaining all the counts CYs simultaneously. But this is the algorithm with memory linear in M, logarithmic in N. We're going to look at this problem more closely on the next slide. But let me emphasize that this is, again, just the first problem in an entire sequence of problems, namely the so-called frequency counting problem. Next frequency, this is a 0th frequency. The first frequency adds all the counts here, but that's just capital N, right? So that's nothing interesting. Things become more interesting when considering the second frequency moment, or more generally the kth frequency moment, where we're asked to sum all these capital C's raised to the kth power. These also turn out to admit very memory efficient algorithm, but they're very sophisticated. So what we're going to look at and analyze is an algorithm for the distinct counting problem, an algorithm that uses memory log n. And this is a very funny algorithm because it uses two tricks to save memory, to get memory down from log n to log n. First trick is we're not asking for the exact number anymore, the exact number of distinct elements, but only for an approximation. Okay. So here for cy, not exactly, but approximate up to factor 2 or up to factor 4, let's say. That's the first trick. Our second trick is our algorithm will use randomization. Now, we already have discussed randomization in chapter 5. So this is a, I think, very interesting application of randomization to save memory and using only approximate counting. So the idea behind this algorithm is to not store the counter for cy, because that would use log n bits of memory in the worst case when y occurs all the time, but instead store and maintain small cy, which is we define to be the logarithm, binary logarithm of the c, capital Cy. Now this is a good idea because the small cy, since its value is at the most log capital N, therefore it only uses log n bits to store this cy. However, there come two obstacles. First, remember that this cy in general is not an integer, right? Because when cy, capital Cy is not a power of 2, then the binary logarithm is not an integer. So instead, we use that cy to approximate the logarithm of capital Cy. Approximately, since we're going for approximate counting. So now imagine that we have in our algorithm stored the small cy as an approximation to capital Cy. And then we see the y's coming by. And when do we need to actually increment this small cy? Put differently, when do we need to proceed from logarithm of capital Cy to 1 plus the logarithm of capital Cy? 1 plus the logarithm of capital Cy is the logarithm of twice capital Cy. That means we need to increment the small cy or stored and maintained approximate counter after having seen the same number of y's as we had seen the last time when we incremented that counter. So whenever the number of y's that we have seen so far doubles, then we need to increment the small y, cy, but we don't know how many cy's we have seen so far because we cannot maintain and store the exact count. Still, that's what we're going to try. We're going to make an algorithm that increments the small cy counter after every capital Cy's occurrence, that is, after every 2 to the small Cy's occurrence of y. And the trick to do that is using randomization. So whenever y comes by in the stream, we're going to flip small cy coins. We have stored small cy, so we can count up to small cy and flip coin each time. And only if all the coins come up heads, then we're going to increment that counter small cy. Why? Well, what is the probability that all small cy coins come up heads? Well, the probability for that is 2 to the minus small cy, because it's cy independent events, each one with probability 50-50, 1 over 2 to come heads, and all of them to come heads is very unlikely probability 2 to the minus cy. Or put differently, the expected number of times we need to see y for all these two heads to come up heads is 2 to the plus cy, right? 1 over probability, that's the expected number of times we need to repeat a process to become successful. One execution, one occurrence of y has probability 2 to the minus cy. After having repeated that 2 to the plus cy times, then we have in expectation, one time happens that all come up with heads. So that's exactly what we want. After expected 2 to the cy times occurrences of y, then we increment our counter. So not deterministically, but in expectation. It's a randomized algorithm. And also it's only an approximate algorithm. Now, how well is that an approximation? Intuitively, it's not a very good approximation, but remember we had devised these techniques for error amplification, and thus by applying this, we can make that algorithm more and more reliable, but it's still always going to be an approximate counting algorithm. The best approximation factor that we can never really achieve is factor 2 because of the logarithm. Actually, one can get arbitrarily close to that, but by repeating that algorithm many times. So that concludes, I think, a very interesting and funny application, random approximate counting to highly memory efficient algorithm with memory use double logarithm of n. Now, I'm not going to say much about the practical use of that. Remember that the single logarithm of n is at most 80 for when n is as much as the number of electrons in the universe. Number of electrons in the universe is estimated to be 2 to the plus 80. The logarithm of that is thus 80. And improving that to a double logarithm, the logarithm of 80, is maybe arguably more an intellectual challenge than actually practically relevant, but the technique itself is certainly interesting, as is its analysis. And that concludes our discussion of chapter 10 on memory efficient algorithms. We motivated memory efficient algorithms with large problems where we large input data and input data that cannot be stored on different levels of the memory hierarchy, including not being stored at all with streaming algorithms. We revisited algorithms for Fibonacci numbers, algorithms with different running times. We revisited them first counting the number of operations and more closely counting the number of bit operations, taking into account how large are the integers that are being added, being compared, being copied, and how large are the integers that are being multiplied using the famous world record algorithm of van der Hoeven. Then we reanalyze these Fibonacci algorithms not from the perspective of running time, but from the perspective of memory use. Again, first counting the number of variables, the number of also implicit during the recursion, and then more closely take into account how large, how many bits does each variable store. And we visited the Boolean matrix powering problem, devising a highly memory efficient algorithm using these two tricks. First, by not counting the input matrix as using up memory. It's provided in a separate read-only part of memory. And secondly, by not asking for the entire matrix power to be returned, but only any desired entry in that matrix power. And we applied that algorithm to the graph reachability problem, arriving at, again, a highly memory efficient algorithm for directed graph reachability, roughly with memory use log n squared. And we saw that this somehow seems to correspond to the parallel running time of our algorithm, parallel algorithm for directed graph reachability. And that led us, after discussing methods and cost of saving memory, namely increasing the runtime time, this similarity of memory consumption of memory efficient algorithms on the one hand, and the parallel running time of efficient parallel algorithms led us to ask, is that coincidence? And Borodin's theorem says from 1977 says this is no coincidence. And Borodin's theorem, the proof was based on this highly interesting method of graph reachability, a new way of looking at algorithm as paths in configuration graph. Finally, we talked about streaming algorithms that cannot store the entire data stream, that can look at the entire data stream only once or a constant number of times. Many statistical information can be obtained from such streams using only logarithmic memory, but interestingly, one can also count the number of occurrences of a given entry using doubly logarithmic memory, so much less. And this was achieved by, again, two tricks. First, by counting approximately, not exactly. And secondly, by harnessing the power of randomization, by flipping coin flips and forgetting the coin flips again. We did not, in this current chapter, discuss I/O efficient or external memory algorithm. That will or may be a topic for future issues of this course. So that's all for today. That's all for this time. That's all for chapter 10. Thank you very much for your attention and see you again. Goodbye.